All right. Today we are going to look into the easiest method for calculating the Fourier transform of a Gaussian signal. Now, you might have seen how some people calculate the Fourier transform for Gaussian signal through some weird substitution. We are not going to do that today here. We are going to apply certain properties of Fourier transform and figure out literally the easiest way for calculating the Fourier transform of a Gaussian signal. And in the end, we shall see we shall have certain realizations about the properties of Fourier transform of a Gaussian signal. All right, so let's begin by again recalling the definition of Fourier transform we have been using so far. The definition that we have been using is that if xt is a time domain signal and if x omega is its Fourier transform, then we define x omega through this complex improper integral here. So this is going to be xt into e to the power minus j omega t dt. So we define our Fourier transform through this, and we define our inverse Fourier transform through this. But again, whatever we are going to discuss today is going to be applicable for any definition of Fourier transform. If you define it differently, the methodology will still be the same. The results will be slightly different, but it will be very similar in nature. All right. So now, what we are going to do today, we are going to find out the Fourier transform of e to the power minus t square, a signal that somewhat looks like this. And again, we are going to generalize this. Okay. So the signal that we are going to talk about is a Gaussian signal. Also, some people might be familiar with this signal by means of normal distribution. Okay, this is one form of a normal distribution, and the signal kind of looks like this. Okay, this is also known as the bell curve, for example, right? So this is my xt in this, right? All right. So now, of course, trying to find out the Fourier transform by just doing the integration would be impossible for us. Okay, I mean, rather very difficult for us, and it might require some weird substitution. Okay, all right, we are going to avoid that. But in order to avoid that, we are going to apply two properties of Fourier transform. Okay, the first property that we are going to discuss, going to use here in calculating the Fourier transform of a Gaussian signal is this one: is that if the Fourier transform of xt is x omega, then the Fourier transform of the time derivative of the signal is j omega multiplied with x omega. So this is called the time differentiation property, or rather the time derivative property. And we are going to apply, also use the frequency derivative property here, and which is, if the Fourier transform of xt is, again, I'm just repeating myself here, if the Fourier transform of xt is x omega, then the frequency differentiation property tells me that the Fourier transform of txt would be j dx omega and d omega. And while we are at it, let's write this as dxt dt. All right. So you're going to use these two properties, and this is called the frequency derivative property. All right. All right. So let's again go back to our goal. Our objective here is to find out the Fourier transform of e to the power minus t square, something like this one. All right. So this is my xt. This is a signal for which I am calculating the Fourier transform, right? So with that said, let's calculate the time derivative of this signal. So dxt dt, that's going to be minus 2t e to the power minus t square, and keep that in mind. All right. All right, fine. So our objective here is to again calculate x omega, where xt is e to the power minus t square. So x omega would be the Fourier transform of xt. All right. All right. So by application of the time derivative property, we can now say that if the Fourier transform of e to the power minus t square is x omega, which I don't yet know, then the Fourier transform of minus 2t e to the power minus t square, and this is the derivative of e to the power minus t square, then by application of the time derivative property, we know that this is going to be the Fourier transform, right? If the sorry, if the Fourier transform of e to the power minus t squared is x omega, then the Fourier transform of the derivative of e to the power minus t square with respect to t, which is minus 2t into e to the power minus t square, that's going to be this j omega into x omega, right? So let's say this is my equation number 1 here, all right? Now again, look at this in a slightly different way, okay? So we again know that the Fourier transform of e to the power minus t square is x omega. But now let's apply the frequency derivative property. So by application of the frequency derivative property, we know the Fourier transform of t into e to the power minus t square. So this is txt. That's going to be j and frequency derivative of x omega. So that's the frequency derivative property. All right. So now, of course, we can multiply both sides with minus 2. So I have minus 2t e to the power minus t square, and the derivative and the Fourier transform of this is going to be minus 2j dx omega d omega. All right. All right. All right. So this is equation number 2. So now, very carefully, let's compare equation number 1 with equation number 2. In equation number 1, we have the Fourier transform of minus 2t e to the power minus t square, okay, and that's j omega x omega. And again, equation number 2, we once again have the Fourier transform of minus 2t into e to the power minus t square. And now here, the Fourier transform is being given as minus 2j x omega d omega, right? But since this is an identity, the right hand sides of equation number 1 and equation number 2 should be identical. And based on that, we can now say that j omega into x omega is equal to minus 2j dx omega d omega. All right. So of course, since j is a constant quantity and non-zero constant quantity, I can just cancel that out, and I would have omega x omega, and that would be equal to minus 2 dx omega d omega. All right, that's simple. All right, so now let's rearrange this differential equation. I shall bring this x omega down in the denominator of dx omega, and let's write this. Okay, so we have dx omega by x omega, and this is equal to, this is going to be equal to minus half omega d omega. I think it's fine, right? All right. So we basically have a differential equation, and we are going to solve the differential equation. And once we solve the differential equation, we would have a certain expression for x omega, and that would be the Fourier transform of e to the power minus t square, right? So let's integrate this. Okay, so let's integrate on both sides, and of course, while doing the integration, we would encounter a constant for integration, and just to avoid that, we are going to turn this integration into a definite integral, right? So omega varies from 0 to a certain value of omega, say, for example. Again, we should have used certain dummy variables, but let's break mathematics for a little bit. We could use a dummy variable here, okay? But let's say the integration varies from the limits of the integration, bounds of integration here is from 0 to omega. Of course, when omega is 0, the value of x omega is of course x0, and when omega is omega, the value of x omega is x omega. Again, we should have used certain dummy variables here, but we are not doing that. Okay, same thing. Okay, so we have done this definite integral in order to make sure that we don't have any constant of integration. But if we really did do the indefinite integrals, then we would have a constant of integration, and then we would have to calculate the value for the constant of integration by making sure that we utilize the fact that when omega is equal to 0, the value of x omega is x0. Same thing, okay? So equating the lower limits would yield the constant for the integration, right? All right. So of course, you understand that this is dx omega divided by x omega. So of course, the integral of this is going to be the natural log of x omega. And of course, this is going to be evaluated from x0 to x omega. And of course, this is going to be half omega square. And we already have a minus half outside. So this is going to be minus 1 by 4. And that's going to be omega square evaluated from 0 to omega. So that's going to be omega square. All right. Then let's put the limits here. On the left hand side, we have log x omega minus log x0, right? And we have minus 1 by 4 omega square here. All right. So it's a difference in logarithms, and by the property of logarithms, we know that this is going to be a quotient of the indices, and that's going to be this. All right. All right. So I'm out of pages. Hold on. All right. Of course, now with this, I can get rid of the natural logarithm and use the definition of the natural logarithm to write this. All right. And thus, my Fourier transform would be x omega, which would be equal to x0 into e to the power minus 1 by 4 omega square, right? So we are already at the end of the Fourier transform. Actually, all we need to do right now is to calculate the value of x0. But in order to calculate the value of x0, let's recall the definition of Fourier transform, right? We defined the Fourier transform x omega as this integration from minus infinity to infinity on xt e to the power minus j omega t dt. And of course, by that definition, x0 is going to be the same thing. Again, this is an identity, okay? It's from minus infinity to infinity. We just put omega equal to 0, and putting omega equal to 0 gives me 1 here. So that's going to be the total area under xt, right? This is the total area under xt from a time span of minus infinity up to infinity, right? All right. So here in this particular scenario, we have the integration from minus infinity to infinity on e to the power minus t square and with respect to t, of course. Now again, there is no antiderivative of e to the power minus t square, right? So we cannot just calculate the antiderivative and put the limits, right? So that is not applicable here. So you have to figure out some other way, okay? So let's try doing this. Let's do some substitution. Let's consider this substitution. Say, let's do this substitution. Say t square is equal to z, okay? And let's differentiate both sides. So we have 2t dt, that's equal to dz, and from that we have dt is equal to half t dz, and t will be root z, square root of z. So dt is equal to 1 by 2 root z dz, and that's just 1 by 2 z to the power minus half dz. All right. All right. And of course, when t is minus infinity, so before this, let's do one more step. Let's realize the fact that this e to the power minus t square is an even function, right? Is an even function. Since this is an even function, this property holds. I can change the integration, bounds of integration to 0 to infinity, and we can write it 2 here, right? Since this function is an even function, right? So we can do that. And after this, let's do this substitution here. And we have, so again, when t is 0, z is 0. When t is plus infinity, z is also plus infinity. All right. So let's do this substitution here. So we have from 0 to infinity, we have e to the power minus z, and on dt, on place of dt, I shall write half z to the power minus half dz, right? All right, that's quite suitable here. So this half cancels out with this 2, and we have integration from 0 to infinity, z to the power, integration from 0 to infinity, we have z to the power minus half e to the power minus z dz, right? All right. All right, we have that, right? And we can rewrite this as integration from 0 to infinity, z to the power plus half minus 1 into e to the power minus z dz. Now recall something very interesting. Okay, recall the definition of gamma functions. Okay, so the gamma function, gamma n, is defined as this integration, right? So gamma n is defined as this. All right, so because of this definition, we can say that this is nothing but gamma half, and this is a very popular point for evaluating gamma functions. This can be evaluated in various ways, and I'm not going to go into that. You can look up the derivation here. This can be done through beta function, this can be done through certain formulas here, this can be done through a double integration. Anyway, so the value for gamma half is known to be root pi, and that is what we have been calculating, right? So we have been calculating the value of x0, and x0 turns out to be root pi, right? So we are kind of done here. So we know that the Fourier transform that we sought out to calculate here was x omega, and that was equal to x0 into this, and we just calculated that x0 was root pi. So this is going to be the Fourier transform here, right? So just to recall, we just realized that the Fourier transform of e to the power minus t square, the simple Gaussian function, is this: root pi e to the power minus 1 by 4 omega square. Okay, but let's not end things here. Okay, let's continue a little bit, right? Let's see if we introduce a constant, right? If we introduce a constant, so now from this, let's say I want to calculate the Fourier transform of e to the power minus t square, that's right, e to the power minus t square by 2 sigma square, right? I want to calculate the Fourier transform of that. So what will that be? What will that be? So in order to calculate that, let's recall a certain property of Fourier transform once more. Okay, and this time we are going to look into the property known as the time and frequency scaling property, which states that if the Fourier transform of xt is x omega, then the Fourier transform of xat, where a is any constant scalar quantity, right? Any constant scalar quantity, then other than 0, of course, then it's going to be 1 by mod a x omega by a. So this is called the time and frequency scaling property. And we did actually prove this in one of our earlier classes. All right, all right. So we're going to apply that. Okay, so to do that, let's see that this actually can be written as e to the power minus t by root 2 sigma whole square. Okay, and just to, okay, let's forget that. Okay, right. So this is the scaling factor here, right? So my objective is to calculate the Fourier transform of e to the power minus t by root 2 sigma whole square, right? We are calculating that. Okay, of course. And we are going to apply the time and frequency scaling property here. To do that, we have to understand that here the scaling factor with time is 1 by root 2 sigma, right? So here basically we have A equal to 1 by root 2 sigma, right? We have that. So with that said, let's apply this property here. So I have 1 by mod A, okay? And just for this particular example, let's say sigma is positive, right? Sigma is a positive quantity, right? So with that said, I would have 1 by mod A, and mod A would be 1 by root 2 sigma, since sigma is positive, so this gets a positive value. So root 2 sigma, we have that, right? Yeah. And here I would have x omega by, let's write that, x omega by 1 by root 2 sigma, all right? And this, all right, and this actually becomes root 2 sigma. And what was this? What was x omega here? All right, x omega was root pi e to the power minus 4 minus 1 by 4 omega square, right? So I would have a root pi here. I would have a root pi here. And I would have e to the power minus 1 by 4. And instead of just having omega square here, let's just write it here once more. So, okay, before going into this, let's simplify this a bit. So I would have root 2 sigma here, and this is x root 2 sigma omega. That is what we are going to have, right? All right. So this is going to be root 2 sigma, and x omega was root pi e to the power minus 1 by 4 omega square, right? This was x omega. Now I have x root 2 sigma omega, right? So I have to multiply everything, multiply omega with root 2 sigma, right? So I would have root 2 sigma omega whole square. So I would have root 2 pi sigma e to the power minus 1 by 4, and here I have 2 sigma square omega square, all right? So simplifying this a bit gives me sigma root over 2 pi e to the power, so this gives me half sigma square omega square, all right? So what we just calculated is the Fourier transform of e to the power minus t square by 2 sigma square, right? So we calculated the Fourier transform of e to the power minus t square by 2 sigma square to be sigma root pi e to the power minus half sigma square omega square. Okay, and if we bring this scaling factor to the left hand side here, this amplitude scaling factor here, we would have 1 by sigma root 2 pi e to the power minus t square by 2 sigma square, and the Fourier transform of this would have been e to the power minus half sigma square omega square. And some of you might already realize that this is the function for standard normal distribution, right? We call this standard normal distribution or standard Gaussian distribution. All right. So this has the this signal has this Fourier transform. But important point to note here is that the Fourier transform of a Gaussian signal is also a Gaussian signal, right? So we have been seeing this. Okay, at the very beginning we saw that the Fourier transform of this simple thing e to the power minus t square turned out to be something that looks very similar to e to the power minus omega square, right? So the Fourier transform for Gaussian signal is another Gaussian signal, right? So this ends this particular problem, but before we actually end this discussion, let's see a certain demo here, right? All right. So but notice very carefully is that this sigma square here in this Gaussian distribution is the standard deviation, right? This sigma is the standard deviation, right? The sigma square is the variance, Okay, right? So this sigma for the Gaussian distribution, that tells you about the width of the Gaussian distribution, right? So if sigma, or the standard deviation, or sigma square, the variance, is large, then it tells you that the width of the Gaussian distribution is larger, right? Something like that. And accordingly, here on the right hand side, for the Fourier transform, the sigma, or rather sigma square, appears in the numerator alongside omega square, right? Okay, this indicates that if the width of the time domain signal becomes larger, then the width of the frequency, the Fourier transform, or the signal in frequency domain, actually reduces. Let's see that in action with a simple demo here. Let's jump. Let me jump to this. All right. So we have a very simple demo here, right? And this is again showing you. So this is the original signal here. So this is xt, and this is its Fourier transform. So here in this axis we have frequency in radian per seconds, of course. In this axis we have time. This is amplitude, and this is the x omega, right? And as you can see, the Fourier transform of a Gaussian signal is a Gaussian signal, right? And as the width of this Gaussian signal becomes larger, the width of this one becomes smaller and smaller. But what if we go to a limiting case? Okay, what if we go to a limiting case? For example, if we make the value of sigma very small, then this Gaussian signal essentially becomes a unit impulse, or a Dirac delta. Okay, a unit impulse. So if we make this sufficiently small here, what we essentially have for xt is the Dirac delta, or the unit impulse. And as you can see, or as you already know, the Fourier transform of Dirac delta, or unit impulse, is a constant, okay, and it has a value of 1. So you know the Fourier transform of delta t is 1, and that is what you can see here, right, as a limiting case of the Fourier transform of the Gaussian signal. Okay, when omega tends to 0 plus, you can see that the Fourier transform of, here on the right hand side, you can see the Fourier transform is actually tending to a constant signal at 1, right? And that is to be expected, right? And let's consider the other limiting case where sigma is very large, right? So if sigma becomes very large, okay, as sigma becomes very large, this signal here, the time domain signal, has a very large bandwidth here. And with that said, you can see this signal almost approaches a constant value, right? Almost approaches a constant value. And here on the right hand side, you can see the Fourier transform almost approaches an impulse, right? And we also know that the Fourier transform of 1 is 2 pi delta omega, right? So by virtue of that, let's go back here. Okay, as limiting cases, so we just realized that as limiting cases, when sigma tends to 0 plus, we have a limiting case, right? The limiting case is basically this 1 by sigma root 2 pi e to the power minus t square by 2 sigma square. This essentially becomes delta t when sigma is very small, right? And its Fourier transform, which is this one, e to the power minus 1 by half sigma square omega square, this becomes 1. As a limiting case, we have seen that for very small values of sigma, okay, and that's to be expected. We already know the Fourier transform delta t is equal to 1, right? And let's increase the pages here. Okay, and as another limiting case, when sigma goes to positive infinity, then this signal, again 1 by root 2 pi, 1 by sigma root 2 pi e to the power minus t square by 2 sigma square. Okay, so when sigma actually tends to positive infinity, of course, this, if you just if you just calculate this, okay, and if you see when sigma actually goes to infinity, goes to positive infinity, so if you calculate this, you will see that this is the scenario we get. Okay, here, when sigma becomes very large in this scenario, okay, So we get a constant value. Simply we get a constant value, right? All right. So if we increase this, we get a constant value, right? Yeah, understandably. And you can verify that, right? And this constant value would be 1 by 2 pi. Okay, when sigma becomes very large. And when sigma becomes very large, what about this quantity? What about this quantity? E to the power minus half sigma square omega square. That becomes delta t. And that is again to be expected because we know the Fourier transform 1 is, sorry, that's going to be delta omega, right? That's to be expected because we know that the Fourier transform of 1 is 2 pi delta omega. So the Fourier transform of 1 by 2 pi is delta omega, right? And we actually are seeing that here. So let me go back to this. Okay, so that is why what we see here, when sigma becomes large enough, then the Gaussian signal here, or time domain Gaussian signal here, becomes a constant, and the amplitude is 1 by 2 pi, of course, here, and the Fourier transform here is a unit impulse. So that ends today's module here. So thank you very much for being here.